Would you believe that when it comes to ski jumping, aerodynamics plays an important role? In fact, the aerodynamics of skis are arguably more complex than wings. That is partly because of the general shape of the skis, but also because they can rotate about the skier's ankles. So depending on how the skier is holding his or her ankle, the aerodynamics changes dramatically, as we will see. And in competition jumping, these changes can make the difference between being first and being first loser, which is also known as second. And the ski jumping circuit is vicious because getting second can bring shame upon you and everyone who's ever known you. So no one wants to get second, everyone wants to get first. So how do the ski aerodynamics affect that? That is what we're looking at today. So first of all, what are the flow physics of the skis? And secondly, how do different orientations of the skis affect that? To answer these questions, we're looking at this paper called Performance and Biomechanics in the Flight Period of Ski Jumping, Influence of Ski Attitude. And this is open access, so you can find the link below. Now, one thing I didn't know was that apparently the ski jump is scored by the judges not just on distance, but by style as well. I'm a little surprised about that because I thought it was just about distance. I mean, I thought you could just strap on a helmet and cannonball down, but apparently it's also style. So anyway, the researchers say that the flight distance of the skier is related to the weight of the skier, the aerodynamics during the flight, as expected, and the initial flight velocity. And the aerodynamics of ski jumping isn't a new field actually, because in the 80s, it was thought that the best posture for the jumpers was to position their skis parallel, like in figure 1a, this is called the H style. But then in the 90s, some computer simulations showed that actually positioning your skis like a V, like in figure 1b here, would give you more distance. In addition to this change in the ski position, the way the skier holds his or her body has also changed, and that's because of aerodynamics. So in figure 1a, we see with the skis parallel, the skier was upright, which doesn't make much sense from an aerodynamic point of view because it literally means you have the greatest cross-sectional area you can possibly put your body into. That's a lot of drag. But this posture was selected because it was thought to maximize the takeoff speed, thereby getting a lot of distance. But then a breakthrough happened to the posture as we see in 1b. So this is where the jumper now leans forward, and this makes a lot more sense because it reduces the frontal area, but also potentially allows the skier to produce some kind of lift too with the body, albeit very inefficiently, but it's still better than the upright position, and also reduces drag as well. And some research showed that actually if you could articulate your body well during the entire process, actually the best solution is to jump off in the parallel position, so this left figure here, with an upright body, then apparently exactly 1.3 seconds after takeoff to transition to this flying V. But even then, there is massive variation in the exact posture you could be in during the flying V. Now, as for the general angle of the skis, apparently the highest lift drag ratio is obtained at around 30 degrees, but this is also dependent on the roll. So that is more if you fall to one side, so you like the skis roll to one side or the other, there is less angle, and that means that maybe the best angle is not optimal here at the 30 degrees. Maybe it's something different. And that is where we pick up this research from. So how do different angles of the skis affect the aerodynamics, not just the roll, but the other pitch and yaw? So to find out, these researchers used CFD, which makes a lot of sense here because it would be very hard to do this experimentally, especially when you try to keep the skier in one position. And in figure 2, we see the setup of their skis, and the rotation of the skis were the major focus of this research. So those familiar with any aeronautics will completely understand the rotation notation, where the skis can pitch, which means they can tilt up like this way. Then it can also roll, which means that they like fall to one side or the other. Then they can also yaw, which means that they rotate backwards. So back in figure 1 here, this angle here between the two skis gets wider. So this diagram is a little confusing, but it is that simple and it's the same as an airplane. So let's move on to their CFD setup to see how they went about it, because there are some interesting points here. So in figure 3, we see their domain and the general setup. First of all, the domain is spherical, and you don't see that every day actually. So usually you use a spherical domain when the flow is hitting the object inside, and that means that the flow can vary a lot if it's a very weird object. So here what they are doing is keeping the mesh exactly the same between runs, but just changing the inlet angle. In addition to that, the sphere nature of the domain means that it's better when the flow is exiting at a variable angle too, so you get less errors with this general domain. So in contrast, let's say you have a car. Well, the flow is moving in one direction really, and there are just small perturbations because of the various wake structures. But overall, the wake of the car is in one direction, which is in the free stream direction. For the skis, there may be some hardcore redirecting going on, we don't know, we need to see that later. But if so, then the sphere domain will be good as well. As for the mesh, as you'd expect, as you get closer to the ski, it gets finer and finer. So the ski is like right in this tiny little section here, and the mesh gets finer and finer. That's good. And one thing that they say is that they used hexahedrons mostly for the mesh because it helps the simulation converge. Now, you can see the outer part is more like a poly, but then inside is the hex, and that's pretty good. So what they mean is that with this hexahedron approach, you can get a better quality mesh, but also track the highly non-uniform flow through each cell better. That ends up with a much more accurate result and much more robust. Now, the Reynolds number based on the skis and the 30 meter per second free stream flow is about 5 million, so the flow should be fully turbulent. Now, they give some finer details about the mesh, and honestly, I have no experience with CFDing skis. I know, why haven't I been CFDing skis all this time? What have I been doing in my life? But anyway, I can't say for sure if these details are good, so I'm just going to use good general CFD practice guidelines and general CFD experience. So they say that the boundary layer had 12 layers, and that is of hexahedrons. That is definitely in line with what regular boundary layers use, so that is good. The Y plus was about 1, which is good because they use the KMega SSD terminus model, so this is a great Y plus to have. Now, one weakness is that they only used steady state RANs, which, given that their skis are bluff bodies, there will be some transient flow features off of them which won't be captured with RANs. As such, this is going to result in some inaccuracies because of this approach. Another thing that is going to lead to some inaccuracies is that, from what I can tell, they only CFD'd one ski and not two skis. So in terms of the flow physics, near the top of the ski, I don't think it would change very much, but at the back of the ski, where they will be very close together as they would be in the V position here, you can see like here they're quite close together, I think there would be some significant interactions, and that would change the flow physics a little bit. So only doing one ski limits the practical applicability of this research. Anyway, the researchers used a total of 1.3 million cells, which is very low. It would take like an afternoon to converge with RANs, but I understand their choice because they looked at a bunch of different angles, as we will see. So if you tally up all the CFD that they did, perhaps this was the finest they could go given their resources. Also, perhaps they didn't need any more cells. We'll have to see what their mesh independent study looked like later. Oh, at least let's go there now actually, let's jump there. So in figure 4a, we see the effects of increasing the number of cells, and they did a good job here because they went from 300,000 cells up to about 2.4 million cells. Let's zoom in a little bit. And they found that 1.3 million cells was where the lift and drag coefficients for this particular ski setup converged. So going above that changed the results by a few percent, but I guess they deemed 1.3 million cells enough. Looking at this graph, I personally would have gone probably higher because it does seem like the 1.8 million cells does change a little bit still, but perhaps they were strapped for resources. I mean, they did apparently do 125 different ski attitudes, as you'll see later, so they probably needed to compromise there. So I think this mesh is independent to within a few percent for the lift and drag coefficients. Now in figure 4b, we see the validation with their experimental data. Now we get something a little bit weird. I'm not sure if I'm reading this right because it's a little strange, but from what I can tell, for the mesh independent study in figure 4a, the researchers had their skis at a pitch angle of 30 degrees and the roll at 15 degrees and no yaw. Then for the validation in figure 4b, they then changed their ski setup so that the roll was now 0 degrees instead of 15 degrees. They did this to match the experimental data they had, but then that makes me wonder why they didn't do that mesh independent study with this setup too, with no roll. Did they do the mesh independent study then realize that the experimental data was different for a different setup, or did they do the other setup and then it didn't agree well with the experimental data they had, so they picked one that did? I don't know, it's weird. Anyway, the safety results are with the solid outlines, so these ones here, and the experiments are with the dotted outlines, so the right columns. The lift coefficient is pretty good. It's within 2.6%, but the drag is quite off. It's about 13.3% off. So from this validation study and the mesh impedance study, I'm not sure how much we can trust the forces. If the forces change by like 20%, then I think that would be okay. But if it's like 5% change, then I think that would be in the error of the CFD, unless trends are following each other all the time, in which case we could probably trust them a bit more. Otherwise, I think that we should focus mostly on the general flow physics and general trends, and the big changes in the forces, not the small changes. Now, just as a quick side note, if you want to learn how to do CFD better or OpenFOAM, which is a really good and free CFD software but hard to learn, take our courses linked below. So let's move on to the results now. In figure 5, we have a really nice plot. There is so much information packed into it, and it is a very easy way to understand it. Remember that these researchers tested 125 different setups, and to convey all this information is difficult. But here they've done a brilliant job. Let me explain what we are seeing here. So there are 6 subfigures ranging from A to F, A, B, C, D, E, F. And these correspond to the force and moment coefficients of a ski at each angle combination. So we see, let me zoom in here a little bit. So we see for the x-axis, this one right here, the alpha, that is for the pitch. Then we have for the y-axis, beta, which is for the yaw. Then for the z-axis, we have gamma, which is for the roll. At the bottom of each figure, we have the color bar, and it ranges from white to red, and it corresponds to the values for each force and moment coefficient. So we have a lot of information here to glean very quickly. It's very effective. Now, in terms of the lift coefficient, generally as expected, increasing the pitch angle increased the lift coefficient. For example, at 0 degrees, we see the values between 0 and about 0.25, depending on the yaw and the roll. But then at 30 and 40 degree pitches, we see lift coefficients constantly above 0.5. That makes a lot of sense. So we can conclude that, as expected, that increasing the angle of attack increases the lift coefficient. That's very logical. One thing that perhaps is a little surprising is that at very high angles of attack, like 40 degrees, the ski is now still producing a lot of lift. That's a bit strange because if you go for other objects, usually you'll get stalled by then, but we don't get that really here from what we can see. So we'll need to see later why that is. As for the yaw, so the beta angle on the y-axis, the general trend is that increasing it also increases the lift coefficient. Again, we are only looking at the forces here, so we don't really know why that's happening, the flow physics behind it, and we'll see later more information about it. But here is just the finding means that if you move the ski back, so you yaw it more, that means that the side edges more and more towards the incoming flow and actually increases the lift coefficient for some reason. Now, increasing the roll of the ski, so this gamma angle on top here, also increases the lift coefficient up to a certain degree. And that makes a lot of sense to me because as you yaw the ski, as you roll the ski, you now have a larger leading edge effectively, and it is similar to the delta wing where you roll the ski more, that now pitches the ski up more to effectively a high angle attack. So in essence, you have this high angle attack, even though the original coordinate system where alpha was the angle attack doesn't really play a factor here, and you have more the gamma, which is taking over for the angle of attack. So we see here that the yaw and roll work together, and increasing both of them, especially at lower pitch angles, increases the lift coefficient. From this figure, I would say that the yaw has more of an effect than the roll though, but both are important. And from this subfigure, it seems like the greatest lift coefficient occurs at a pitch angle of about 30 degrees, a yaw angle of about 25 degrees maybe, and a roll angle of about 0 degrees. And that gives a lift coefficient of about 0.8. But when you're flying through the air on skis, the lift coefficient isn't the only thing that will govern how far you will fly. The drag coefficient is also important because the lower the drag, the faster you will continue to travel. So the further you go as well. So in figure 5b, we see the effects of these different angles on the drag coefficient. As expected, literally any deviation from the ski pointing directly into the flow results in a higher drag, a drag coefficient, And that makes sense because the more you angle the ski to the flow, whether that is in the pitch, the yaw, or the roll, the more of a bluff body it will become. Whereas if it's right into the flow, it's very streamlined then, at least relatively speaking. Now, interestingly, from this figure, it seems like the yaw and roll angles are almost equally effective at increasing the drag coefficient. So, for example, at a pitch angle of 10 degrees, so this second figure, this second slice going through, if you yaw that ski up to about 40 degrees, and then the drag coefficient increases from 0 to about 0.2. And that is the same amount as when you roll the ski from 0 degrees to 40 degrees. Perhaps it's a touch lower, maybe it's like 0.17, but still, they're very similar. However, that's the drag coefficient. And when you consider how far the ski will fly, the drag coefficient isn't everything because the drag is also proportional to the frontal area. And when you roll the ski, the frontal area doesn't change. But when you yaw the ski, the frontal area does change a lot because you expose the very long side more and more. So the frontal area gets very large very quickly. So if you factor in the frontal area into the drag, yawing the ski has a far more detrimental effect on the overall drag than rolling does. So sure, you can have more or less the same drag coefficient between the yaw and roll, but the frontal area is like 5 times more for the yaw, so the drag will be like 5 times more. Now for the pitch, the drag coefficient is also very sensitive to it, as you would expect. It literally any increase results in an increase in the drag coefficient too. And it also will increase the frontal area as well. So it's worse on both worlds. The worst is at a 40-degree pitch, a 40-degree yaw, and a 40-degree roll here. So like that point right there. So everything is maxed out, and the drag coefficient is like 1.0. Now in subfigure 5C, we see the lift to drag ratio, and this is a little more indicative of how good the ski is. A higher lift to drag ratio will result in a higher glide ratio because the ski doesn't need to drop as much to gain enough kinetic energy to overcome the loss in velocity due to the drag. So what this means is we want as high a lift to drag ratio as possible. The higher that is, generally the further you'll go. In this subfigure, we see that the best values occur for a 0 and 10 degree pitch angle, so these first two slices. But expectedly, the 0 degree pitch angle is a little more erratic because the lift coefficient is so low to begin with, and minor changes to it results in major changes to the lift to drag ratio. Looking back at this plot, look at all these very low lift coefficient values. On the other hand, at 10 degrees, the ski is far more stable, where small changes in any of the angles doesn't change the lift to drag ratio too much. So from a practical point of view, the best lift to drag ratio occurs for a pitch angle of about 10 degrees. A yaw angle of about 10 degrees, and a 0 degree roll angle. That results in a lift to drag ratio of about 3.2-ish. And I say that that is the best practical lift to drag ratio because at 0 degree pitch angle, we see a lift to drag ratio of up to 4.5 or so right here in that juicy region. But if you change the roll angle by even 5 degrees, it drops to like 2.3, so you almost halve what you had. So trying to hold that perfect angle during flight would be super difficult, and there is little margin for error. On the other hand, going to the optimal configuration we saw for the 10 degree pitch angle, minor changes in the yaw or roll don't really result in as much of a loss. So you have a greater margin of error, and hence it is more practical. You can hit that much more easily. So here the drag coefficient is overriding the lift to drag ratio. It's really playing the major component here. In terms of the 3 moment coefficients, let's zoom out a little bit here. Here we go. So they're all pretty good in that they don't change too suddenly with any minor changes in angles. The yaw moment in figure 5E here is very insensitive to really any change in angle. So with the maximum value being like 0.08 and the minimum being like minus 0.05. Contrasting that to the pitch moment in the subfigure 5D here, we see large changes to it when increasing the pitch angle. There are also minor changes when changing the other two angles, which shows perhaps some level of inertial coupling. Then the roll, so this figure here in 5F, shows that there is some variability, but not as much as the pitching moment. What all of this tells us is that for the ski jumper, you would have to keep an eye more on the pitch than anything else because of its tendency to balloon out. Once you're on a bit of more of a pitch, it's going to just keep trying to rotate you over that pitching moment. The good thing is that because the yaw moment coefficient isn't so large, the skis aren't being forced out as much, relatively speaking, which means your groin muscles aren't going to get stretched too much. So those are the forces of the moment. But what about the actual flow physics of the ski? So in figure 6, we see the flow physics when changing the pitch angle. And I'm happy in that the researchers here know their fluid mechanics because they say that with the ski here, that should be exhibiting a symmetrical vortex pattern, very similar to a delta wing, where you have one large vortex on each side of the ski, and that then complements each other. They're counter-rotating, sorry. It's pure delta wing flow physics going on here. And actually, if you don't know about the flow physics of a delta wing, check out our YouTube video called Aero Fundamentals number 43, Delta Wing Explained. We go through the aerodynamics of it there. Now, for this ski, we don't actually see the exact same flow physics as a delta wing, and that is for a very good reason. So this is because the yaw angle isn't 0 degrees, it is 20 degrees. So one side of the ski is at a different angle to the oncoming flow to the other side. that asymmetry doesn't result in one vortex being stronger than the other. Instead, it results in many vortices forming. So you not only now have just a single pair, there are now 3 pairs. That is quite unexpected. As shown in subfigure 6a, there is literally a triple vortex system happening, running down the entire ski, and this is for a 10-degree pitch angle. As the pitch angle increases, so B, C, D, the vortices get larger and larger and arguably stronger, because if you look at the pressure on the ski, so the top of the ski here, the blue, it drops a lot. So it goes not too bad, pretty bad, really bad, and not too bad again. So that is a strong indication that the vortices are getting larger. And it makes sense because that is what happens with the delta wing too. So even though we have just 3 pairs here, I think the same kind of thing is happening where the flow rolls up around the edges. So it seems like the general flow structure is akin to a typical delta wing, but there are just now 3 sets of vortices. Now, like a delta wing, I would expect that at some pitch angle, the vortices will pop. They're not shown here too much because the largest pitch angle is only 40 degrees. Maybe there is a little bit of popping happening because the pressures drop, but if you go to like 60 degrees or higher, these vortices will probably pop completely. So knowing that this vortex system forms, the lift being produced on the ski is likely some kind of vortex lift, and the low pressure cores on the vortices suck the air down more and allows the skis to produce lift at much higher angles of attack. Like even at 20 degrees, these skis should be stalling if it wasn't for these vortices. And in fact, in subfigure 5a, we did see that even at 40 degrees, there was still a lot of lift being produced. So right here, and that's probably because of this vortex lift. What about the effects of the yaw angle though? So in figure 7, we see what happens when you go from no yaw, so here, to 40 degree yaw. And note that this is for no roll either. Let's zoom in a little bit. So that's figure 8, figure 7 here. That's the one we're looking at. So the pitch is quite a lot, it's 30 degrees. And with no yaw, we get the familiar delta wing pattern where you have 2 large vortices, one on each side, and they run along the entire length of the ski. Then yawing to 40 degrees produces the 3-pair vortex system that we just saw. In addition to that, the top surface of the ski is much lower pressure. You can see along the entire thing it's like minus 200 maybe to minus 500 compared to 0 to minus 500 right at the tip. So arguably, this multi-pair vortex system is much better at producing lift than the single vortex pair you get over delta wings. And that makes sense to me because there are 3 times the vortices. That means that a lot of low pressure is over the ski. And that is also why in subfigure 5a, increasing the yaw angle increased the lift coefficient as well. As we saw right here, increasing the yaw angle increased that lift coefficient as well. So that's all good, that's all in agreement. Now finally, what about when the ski rolls? How does that change anything, if it does? So in subfigure 5a, we saw that the lift coefficient increased up until a certain roll angle, and usually about at 20 degrees, it then reduced with even greater roll angles. Why is that? Well, now things get funky. So in figure 8 here, this is for the roll. Let's zoom out a little bit. That's too much. There we go. So we see changing the roll angle from 20 degrees on the left to 40 degrees on the right. And one thing I don't like is that this is also for a yaw angle of 20 degrees and not 0 degrees. So we haven't decoupled the roll from the yaw. The yaw is still playing a bit of a role here. Anyway, so because of the yaw, it seems like we still have the triple pair vortex system forming, but it is unclear what is exactly happening. The authors say that for 20 degrees, the vortex system is as you would expect, but when you increase to 40 degrees, the pattern reverses in that the side that had the smaller vortices now get the larger vortices. At least that is what I understand of it. So this here, let's zoom in a little bit. So originally, this vortex was stronger, or bigger at least, now it's smaller. As I said, it's a little funky. With that, apparently the pressure imbalance between the top and bottom surfaces of the ski reduces, going from 20 to 40. I'm not exactly sure why, but it might have something to do with one edge of the ski tilting to a sharper and sharper angle to the incoming flow at a faster rate than the other edge. I don't know, I think more information is needed about this particular phenomenon. But for the other 2 angles, the pitch and yaw, their trends make perfect sense. So increasing the pitch angle is obviously going to result in more vortices, stronger vortices at least, and yawing the ski is resulting in stronger vortices too, at least on one side. And with that, we come to the end of this podcast. I thought it was very interesting, and a topic that may initially have seemed to be simple is actually a very complicated topic. And just as a side note, this was all done with CFD, and if you want to learn CFD more, check out our courses below. And if you want to learn OpenFOAM, which allows you to do all of this and a lot more for free, then check out our courses below. And if you're doing experiments, did you know that you have probably a 2 to 4% error in your results and you don't even know about it? The reason why is that the atmospheric conditions that you're testing in constantly change. And in the atmosphere Hawk link below, we go through the math of it and how you can fix that. So that is the end of this podcast. If you liked it, hit the like and subscribe buttons, and we'll see you next one. Peace, amigos.